So the aim of the game is to calculate this thing given that I give you the parameters of the hidden Markov model. And we will actually see in problem 3 that we also need this marginal probability. What's problem 3? Problem 3 is learning the parameters, okay? And that's where we really want to get to. What we want is we want the overall probability. And what you can do is you can get the overall probability by summing up over all the possible sequences through the hidden Markov model. Okay, so this is just the marginalization rule of probability theory, and basically what you're doing is you're saying there's a ton of different ways of getting through this hidden Markov model, sum up all the different paths of getting through it. And one of those paths will actually correspond to the Viterbi path. So one of the paths going through it will be the most probable path. That path will have this value p hat. So in this summation, you'll sum up a ton of stuff, and one of the things that you'll sum up is the p hat that we got from Viterbi land. With a little asterisk that if these things are continuous, then this is a density and it's not actual probability. If these things are discrete, then you're getting the probability of a sequence, the actual real probability, a value that's larger than 0 and smaller than 1, by summing up all the probabilities of the paths through the hidden Markov model. Now we end up with this problem that we faced a number of times before, which is if you consider all possible paths through a hidden Markov model, there is a ton of paths. Okay, if you've got k states and sequence length of t, then in the order of k to the power of t paths. Too many. Okay, so what do? We end up doing dynamic programming again. Okay, and the steps that we will go through now looks almost exactly the same as Viterbi, with one difference, which I will tell you in 1 second. So what we're going to do is, in Viterbi, we defined these delta terms, delta t j, okay? Now what we're going to do is we're going to define these alpha terms, okay? And these alpha terms, let me just scroll up here. For Viterbi, we defined these delta tj's. For the algorithm for the marginal probability, we're defining these alpha terms. Okay. Now the alpha terms, you can think of that as the probability of being in state J after seeing the first T observations. If you want to, you can jump back and go and look at the Viterbi algorithm and see how we defined delta and Tj. I will tell you in a second. This is just the definition for the alphas. And now what we do is, instead of basically coming up with some complicated way of looking at all the paths in order to calculate this, we come up with a recursive formulation, exactly like we did with Viterbi. And the steps we take also looks very similar to Viterbi. Okay, so you end up, you start with this definition of the alphas, okay? And then what you do is you repeatedly apply the chain rule of probability theory, and you're getting bored of this now, but P of A and B is equal to P of A given B times P of B. Okay, you never thought you would use this rule that you learned in, I don't know, kindergarten so much, right? Okay, so what we do is here we've got a bunch of stuff. We've got the sequence, we've got the state, and what you do is you split off the first xt in that sequence. That's your A, okay? And then given all the rest times P of B, okay, and you can think of that as your B. Now, this thing, what we do is we calculate this. So this is the probability of the sequence up to the time step before the time step that we're looking at now. And then this is the state at this time step t right now. Okay. Now, to calculate this, we can take the marginal probability by summing up over the previous state at the previous time step, t minus 1. Okay. This is just the rule for marginal probability. Okay. Awesome source. Okay, and then you can again apply the chain rule. And in this case, the chain rule, our A is this guy. Okay, and then our B is the rest. Okay, and that's left over. So this would be our B. Okay, so B is that and that. Okay, so you get the probability of A given B times the probability of B, but in this B we can chuck away the X because the current state only depends on the state before it. We don't have to look at the sequence. That's the hidden Markov model assumption. Right? Now this thing, That is just the transition probability of going from state I to state J. So that ends up being that. Okay. And then this, if you look at that, that is just the definition of alpha, but for the time step before the one that I'm looking at now, and for state I instead of state J. Okay, so that just becomes alpha t minus 1 I. And we end up with this little equation here. Okay, I went through that pretty quickly because the steps are exactly the same as Viterbi. I've said that a million times. What's the one difference?
The summation.
Nana's got it. The summation, that is the difference. And what is different in the summation? It's a max. Okay, that's exactly right. The equation looks almost identical to the delta. Well, actually, it looks exactly the same as the delta, except instead of a sum here, we've got a max. Okay, and that makes sense because Viterbi tries to find the most likely path. This algorithm, which I will mention in a second, is called the forward algorithm. The forward algorithm tries to find the overall probability, which means even you also need to consider stuff that's not the max in order to calculate the overall probability. So the equation looks exactly the same, and the only thing that's changed is that has changed from a max to a sum. Perfect. Okay, but then I will just say again what I said. In practice, people very often end up using just Viterbi. One reason is it's easier to keep track of some things. The point here is with this marginal probability, you're really considering all the possible ways to get through. We're still not done. We still want to get the overall marginal probability of observing this sequence through our hidden Markov model. Okay, and to do that, we need to incorporate one last step after calculating all the alphas, and that is to go from the your last emitting state to the terminating end of sequence state. So you also need to incorporate that transition probability. So the overall probability ends up being the sum of the alphas up to the time step capital T, and then you make that last transition into the final state. So this last equation here, let's just draw that out. So for state 1, you calculate an alpha at time step T. That's the very, very last actual observation. For state 2, you calculate an alpha. For state 3, 4, 5, 6, up to state capital K, you add an alpha, okay? And then you make this last transition to my final state. That state is state K plus 1. It's the end of sequence state. Okay, cool. And what you have to do is you need to incorporate the transition probability from state 1 to my terminating state, the transition probability from state 2 to my terminating state, all the others, and then also the transition probability from state K to my terminating state. Okay? And in Viterbi, we would have taken the max over all of those. What we do now is we take the sum over all of those, and that gives us our overall marginal probability for this hidden Markov model with that observation sequence. In the end, you get this algorithm called the forward algorithm that gives us the overall marginal probability for a specific hidden Markov model. The algorithm looks super familiar because it looks almost exactly like the Viterbi algorithm. The Viterbi algorithm just has a max there and a max there. One thing is that the initialization here in this step looks a little bit crazy. You don't actually need this initialization in order to calculate the overall marginal probability. But you do need this initialization later on when we get to problem number 3, the learning problem. Then it actually helps, well, you actually need that initialization there. We just do one quick example for the forward algorithm, and I'm not going to spend that much time on it because it is so similar to the Viterbi algorithm, but I just want that one step to basically click in. Okay, cool. So this is actually, again, our hidden Markov model that we used for the Viterbi example. Let's just quickly jump there. This one here. And we're using the same transition matrix and the same emission distribution as we had in this Viterbi example. It's got 2 states. I labeled them V because it's a vowel-like state, and C, which is a consonant-like state. And then you've got these transition probabilities for moving through this hidden Markov model. Okay, so exactly the same hidden Markov model as in this Viterbi example, except now instead of doing Viterbi, we're going to do the forward algorithm, which gives us the marginal probability. Okay, so I'm not going to go through the whole thing again. I'm just going to summarize the key steps. So t is equal to 1, 2, 3. Okay, and then at t0, we're in the start state, okay, with probability 1. And then at t4, we're always going to be in the end state. Okay, and this value here, that is going to give us our overall probability, the marginal probability of observing MOH through this hidden Markov model. The states, you can be in state 0, state 1, state 2, state 3. Okay, I'm just going to pretend like we've run the algorithm for a little bit. So we get 0.6 for that alpha, we get 0.0 for that alpha. Let's just think, what is this alpha? Okay, so this is alpha at time step 1 for state 1. This is alpha at time step 1 for state 2. 0.024, we get there, and then 0.144, we get there. Some of these values will look the same as the Viterbi algorithm if you have 0 probabilities on the other options. But if you don't, then these values will be larger than the Viterbi algorithm. Okay, now let's consider this one here. It's alpha for time step 3, state 1. Okay, alpha for time step 3, state j. You can go through the previous algorithm summary. This is P of x times step 3 equal to the observation, the thing we're actually observing now, which is h. Given that we're in state j, I'll make the j a 1 in a second. And then what we're doing is we're summing up all the possible ways to get to this state from state little I equal to 1 up to big K, the transition probability from state j, I to j, and then the alpha from being in that previous state. Okay, so if j is equal to 1, which means that it's a consonant, okay, or the C state, then we've got alpha 3 of being in the consonant state, P of h given that we're in the consonant state, and then we've got a summation over two things here. So we've got, and it's basically a summation over the two options. We can either come from this way, or we can come from this way. Okay, so the first option is that in the previous time step, we were in the C state, and now we're still in the C state, times the alpha corresponding to that one, which is alpha at time step 2 being in state 1, or state consonant, plus, okay, and then the other option is that in the previous time step we were in V and we've moved now to the consonant state. Okay, so in the previous time step we were in V, now we're moving to C, and then the alpha corresponding to that previous time step. So in that we were in time step 2, we were in the vowel clause. Okay. And you can go back, look up the probabilities. Here we've got 0.2 times, okay? And then this is also 0.2 times 0.024. That value is that alpha value there, plus the transition probability of a vowel to a consonant, which is 0.7 times, okay? And then this alpha here, 0.144. Okay, and you end up with a value of 0.02112. Okay, and that's that alpha value there, 0.02112. And you can fill up the rest of the table in a similar way. And the point here is that I'm considering a summation here, not just the max. So I'm actually adding up all the partial ways to get to this particular point. I give the complete table there. So if you want some fun, go and sit in a bath with some red wine and fill in the table. Enjoy yourselves. Okay, and this number here, this is the overall probability of that observation given the parameters of this particular hidden Markov model. Everyone happy on the inside? Amazing. The forward algorithm basically goes in the forward direction, saying what's the probability of being in a state given that I've observed everything that came before this specific time step? You could have also gone the backwards direction, which feels a little bit weird, but you can actually do it, okay? It's just probabilities, okay? So you can also use the chain rule of probability to go basically from the reverse side, okay? You start at the end of the sequence and you're moving backwards. And in that case, you can define these betas, the backward probabilities. And beta is basically the probability of observing a partial sequence given that I end up in this current state, J. Okay, so just read that equation for a little bit. This is the observed sequence from the next time step onwards up to the end. And this is the state in the current time step that I'm in, J. And the reason we need the betas are for learning. Okay, so we will see in a second that we actually need the betas when we're going to learn the parameters. But the steps are exactly the same for the alphas. The only big difference is that you're going in the reverse direction. Okay, the backward algorithm then ends up looking like this. Okay, so you've got this betas. Again, this funny initialization here we only need for learning, problem 3, which we'll get to in a second. You have your beta at the final time step is just a transition from the end state into a particular state, and that makes sense. Okay, so this is just the transition into state J from my terminating end of sequence state. Okay, and that makes sense as an initialization if we're going in the backwards direction. Okay, and then the recursion you keep on updating, but now instead of going from time step 1, 2, 3, 4, 5, you start at the final time step, or actually the pre-final time step, and then you move to the front of the sequence in the kind of the reverse direction. Okay, and then termination, again, you can get the overall probability, and what you need to do right at the final step for the backward algorithm is you need to incorporate the probability of going from a state into the start state because we're going in the reverse. Okay, so you calculate a bunch of betas. Let's just draw it out here. And then if this is my very first state, state 0, my start of sequence state, then I've calculated a beta 0 for state 1. I've calculated a beta 0 for state 2, and and a beta 0 for state K. Okay, and then we need to make this basically final jump into my terminating state. And to do that, you need to incorporate the transition probability of going from the start symbol to state 1, probability of the start symbol to state 2, and then the probability of going from my start symbol to step K. And then because we're doing overall probability, we basically take the sum over all of those paths, and that gives us the marginal probability of this sequence given the hidden Markov model. Does that make sense? Exactly, just the reverse. Okay, and that all works out. So we've got the 3 hidden Markov model problems. You know how to find the most likely sequence using Viterbi. You also now know how to do the marginal probability. What's the name of the algorithm to do this? Forward algorithm. What's another algorithm that you can use? The backward algorithm. Okay, cool. Algorithm. Okay, and now we're getting to learning.